All right, good morning. Any questions, any comments? So today I want to talk about so-called gauge symmetry. And related to this, we are also going to see flux quantization. So first, let me start with gauge symmetry. Suppose, we are still working within Ginzburg-Landau formalism, and suppose I take my order parameter in Ginzburg-Landau and I replace it with itself times some phase. But this phase is not constant. This phase is what we call is local. Every point in space we are putting like a phase degree of freedom. And what we need to do is, like, of course, if we have like this term and this term do not change because they are phase independent. But we need to think about the gradient term. For the gradient term, so I remind you this momentum operator is minus I h bar del minus, let me keep it like this, q over c a, but remember q, I think I will show you the argument why it is 2e today, but for the moment let's take it to be 2e. Then I want to hit the order parameter with this and see how it changes. So this is going to be minus I h bar gradient minus q over c a times, okay, this one, let me put like an arrow, with this change goes to this psi of r times e to the I theta of r. So what this will be is, this is going to be minus I h bar gradient of phi times e to the I theta plus psi e to the I theta minus I h bar. I can hit on the face and it's going to give me I gradient of theta. And lastly there is this term which is minus q over c a psi e to the I theta. And if I collect everything, I have this e to the I theta. I have this minus I h bar gradient plus h bar gradient of phase minus q over c a, this entire thing hitting on psi. Therefore, if we see that, if we also let this a modify to a plus h bar c over q times gradient of theta, so what we see is this term. This term is going to go to this one minus q over c a minus q over c h bar c over q gradient theta. So you can see this one cancel, and this entire term is cancelling this term, and entire Ginzburg-Landau action remains unchanged. Right? With this gradient term remains the same. What I mean is, in the Ginzburg-Landau term, there is like this minus I h bar gradient minus q over c a acting on psi with this transformation, it goes to itself. I think there's like a square here and square there. And this change, let me just summarize what the change was. We change psi to some psi times e to the I theta. Let me emphasize, this is what we call local gauge transformation. And we also had to change A go to A plus h bar c over q, which is the phase. And of course, there is also like a Maxwell term, which is b squared term, but b squared does not change because it is like an overall gradient, and this entire action remains unchanged. It's called, so this is called, so local gauge invariance. And this is in contrast to global gauge invariance. Global gauge invariance is like when this theta is constant, but this is trivial, right? In our case, if you have like a trivial phase on everything, because everything comes with absolute value, there's nothing to talk about in that case. So sometimes in like more modern terminology, people don't call this gauge symmetry, because symmetry is generally associated with some physical transformation we put in physicists, like rotation, like translation, like inversion. These are all physical changes, like as Feynman says, like change without change, right? But the gauge symmetry is not like that. Gauge is like the way we write equations, right? And whether we have this vector potential or this vector potential with additional gradient is only in our equations. There is no such change in nature. Sometimes in more modern language, people call this gauge redundancy. But I think for us, it is not very important. So, the specialists care about this difference, but let's not get into too much into that. So, in bulk, bulk means uniform, like without boundaries and any gradients. And superconductor has a constant phase, like this theta of R is constant for all R. And this is kind of like a crystal, right? So this is what we call like phase stiffness. Stiffness in the sense like a crystal. In a crystal, right? There's like some, so this individual atom in a crystal is free to choose wherever it wants to. It can be here, here. But once you change the position of this, you need to change the position of entire thing. Right, so there is like some kind of stiffness, and similar to a crystal, we also have like a stiffness. But here we have like superfluid phase stiffness, and typically, so we have this psi of R is some constant, or like sometimes people call this slowly varying function times e to the I theta of R. So the language is like this norm. If you want, I can also put it like this. Psi is, sometimes people call it Higgs. So the variations in psi is gapped, whereas theta of R is slowly varying, and it's also gapless. So the picture is, so if I have I don't know, like some free energy, and this is my psi. So I have this double minima, but in the case of a complex order parameter, we also need to think about rotating this double valve in like in the plane, right? And this is sometimes called Mexican head potential. And in that Mexican head potential, there are two modes. So this one, these kind of like fluctuations of magnitude of order parameter are like, if you want, these are like Higgs modes, and there's like rolling around the minimum, right? There's like a ring, and you can see free energy does not change along the ring. So these are gapless theta modes. And if you look at the free energy, so F is going to be F, like F, let me call it some F is some constants plus d cube r 1 over 2m minus I h bar gradient minus q over c a psi squared. Right, now we put some constant times e to the I theta here, and this action is going to turn immediately this fs0 plus, let me use the notation in the textbook. It's like some constant rho of s d cube r times gradient of theta plus, let me also put 2e over h bar c a squared. And here this rho of s is h bar squared over 2m psi naught squared. Sometimes this is also called superfluid stiffness. And you can see, so this gapless mode, this theta is coupling to electromagnetic field, right? You created like a gapless mode, and this Higgs mode dropped out, right? This is like a high energy mode, whereas this low energy mode is coupling to A. And of course there's also some here there's like 1 over 8 pi d cube b squared term, and this b squared term is gradient of A. There's like gradient of A plus some A squared, right? So in the spirit of like field theory, this is like some gradient. It's not exactly like that, but let me be a little bit careless. It is like, if you want del I, del j, some A plus some m squared A because of this. And you can see we gapped out also the electromagnetic field. Because of coupling to this gapless mode, electromagnetic field acquired mass. Normally magnetic and electric fields, they are like gapless, they are photons. But because of coupling and because of symmetry breaking, we acquired the mass. And that's what we call sometimes Anderson-Higgs mechanism. I think the first person to notice this was Anderson in the context of superconductors, and Higgs recognized what was going on, and he generalized it to particle theory, and he got the Nobel Prize for this prediction. And let me write a little bit formally what's happening. So this theta is arbitrary, but the same in entire sample. You can think of this like magnetization, right? In like a magnet, there's like a magnetization each individual atom has like a little magnetic moment, but when all of them align and they have this rigidity, you have like a macroscopic M. And here this theta is kind of like acting like that. And here I also want to remind you our XY model analogy, where in the XY model this theta is like a planar vector, and this planar vector is exactly like a magnetic vector. So in that case, because we picked a theta, so this global gauge symmetry is spontaneously broken. So this is what we call spontaneous symmetry breaking. There's no reason, the system just picks one and that symmetry is gone. Any questions?
How can we pick this theta?
There's no way you can pick, right? It is arbitrary, but the point is, once you pick one, it is the same everywhere, right? And what is important, we are going to see that what is important, of course this theta is defined up to 2 pi. What is important is not its value at a given point, but the difference between values. And in a little bit you are going to see this is going to give rise to things like flux quantization, and later we'll see Josephson effect. If two superconductors are in contact with different theta, there is going to be like a current, and this current is experimentally measurable. But in like a bulk superconductor, this is arbitrary.
For example, when we say it's spontaneously broken, and there is the meaning.
Exactly, like system goes and picks exactly like in a magnet, right? Think about like a magnet, like here's your magnet, and at high temperatures all of these spins are like arbitrary, and then as you cool down and then cross the so-called Curie temperature, they just align in some arbitrary direction. Of course, if there's like grain boundaries or like there's like some little seed here that like can nucleate all of these alignments, that's going to be source. But if you have like a perfectly uniform sample, any direction is fine. This one is fine, this one is fine. Then system will arbitrarily choose one, and it is going to be the global orientation. And theta is the same. Let's calculate the current. Current J, this is like superfluid current, is given by minus C del F del A. I think we talked about this last time. And if you go and take the derivative of this action with respect to A, right? Now this is standard. What you are going to find is minus 2E over H bar rho of S times gradient of theta plus 2E over H bar C and
I think there has to be some A.
Oh yes. So this is A. And in bulk means there is no boundary, infinite system. We pick like a uniform theta everywhere because that's the symmetry breaking. That means del theta is going to be 0 in the bulk. And this immediately gives us Js is equal to minus, let me also put this back to Q generalized form again, MC A. And this is, does anybody remember the name for this equation? Like who first suggested that current be proper? London, yeah, this is exactly the London equation. And in the London equation, okay, here this NS is psi squared, and we know this is A dot over B Tc minus T. And if you calculate, right, this is 1 over lambda squared. If you calculate the London penetration depth, let me write the, not the square but itself, it is going to be this MB divided by, yeah, there are some factors, let me not write this, this is like E squared A dot. What is important for us is this Tc minus T square root, and it is proportional to, so this Tc minus T over Tc to the minus a half, and we call this reduced temperature to minus a half. And exactly in the coherence length, we also found it to be proportional to this T to the minus a half, and lambda goes to infinity, psi goes to infinity as you approach to critical points, but their ratio, because they both diverge with the same power, their ratio kappa, which is defined by lambda over T divided by psi of T, is some constant, right? Some constant. And it is because it is independent of T. So this kappa, sometimes called Ginzburg parameter, will be a key parameter to determine if you have like a type 1 or type 2 superconductor. But for the moment, we don't need that. Let me give you a couple of examples. So this is, let me give you Tc in Kelvin and lambda at 0 temperature in nanometers, psi at 0 temperature in nanometers, and kappa over lambda. So one of the best understood superconductors is aluminum, and it is Tc is 1.2 Kelvin. This London penetration depth is something like 1500 nanometers, and this is about 50 nanometers, and you can see, oh sorry, this is not kappa over lambda, this is just kappa. Kappa is much smaller than 1, it's something like 0.03. Another one is tin. So this is also like low temperature, 3.7 Kelvin. This is about 180. This is 42, and this is 0.2. This is still less than 1. So lead is also a very well understood superconductor. Critical temperature is about 7 Kelvin. This is 90. This is 40, and this is 0.5.
Is there something wrong with the kappa definition? You said lambda over psi.
Yeah. So lambda is a T-dependent quantity. Psi is a T-dependent quantity. They both diverge with the same power, and if you take their ratio, it's like a constant, independent of temperature.
For example, in the aluminum case, calculation.
Oh, did I?
One of them is reciprocal. I don't know.
Yes. Yes. I think. Let me check my resource. I just copied from the book. Let me make sure this is correct. I think this is. I think the book also got it wrong. So for aluminum, yes, I think. Yeah, I think the book messed up. Very good eye. So I found it from like hyperphysics. It says, I think this one is psi, this one is lambda. Thank you. That's a good job. So this one, aluminum is here 1600, and this one is, yeah, I think in another, so this one is not 180 but 230. Lead is not, 83. But these are, this is probably a little bit more up to date, right? This book is like 30 years old. But now I think this makes sense, right? This side is correct. Good. Thanks a lot. So, but like if you go to some other superconductors like niobium, it's like this is 9, this is about 40, this is about 50, and you can see this is something order 1. Another compound with niobium, like for example niobium 3, germanium. So you can see critical temperature is a little higher, coherence length is a little smaller, but penetration depth is much bigger. Therefore, this is order of 30. And let me write one. So there is like a more complicated chemical formula, but this is what we generally call yubaku. It's like unconventional high TC superconductor. So TC is 90. Coherence length is very tiny, whereas penetration depth is very large. So this is order of 100. And we'll see later that these superconductors are going to be type 1, these superconductors are going to be type 2, and we'll spend some time with that. Good? Any questions? So let me do, okay, I have a little bit more, and I think this is a little bit more exciting, so let me not skip that. Let's talk about flux quantization. And for that, I'm going to consider like a ring-shaped superconductor. So what we have is, suppose, something like that. So this is superconducting region. And inside this, I want to put some solenoid, and I have some flux inside. So this is flux. So this is superconductor. This is hole inside the superconductor. Okay. And magnetic flux phi, we can calculate. Phi is equal to the area dot magnetic field, and we always have the same trick. We convert this using Stokes theorem. Okay, let me also choose a loop. So I want to choose a loop within a superconductor. So this is my C, and this is my C, and I want to take line integral of vector potential. And here you can see I have flux, and inside superconductor I want to choose exactly like superfluid helium. I want to choose this A phi to be non-zero, and since this is like a ring, it's going to be constant inside, and other components AZ and AR to be 0. Then this equation is going to give me this phi is equal to A phi times 2 pi r, and from here I found A phi to be phi over 2 pi r. Good. And also I need to think about order parameter. Order parameter, so this psi, the only variable here is this azimuthal angle. This phi should be equal to phi times theta plus 2 pi, right? If I go one round and come back, I need to have like a single valued order parameter. If I have multiple valued, I don't know which one to pick, so I cannot do that. That's why this psi needs to be of the form some psi 0 times e to the I n phi, right? Some periodic function. And here, exactly like in superfluid helium, so this n is positive or negative integer, and we called it binding number. And exactly like a superfluid, it's like a topological number, right? It cannot change continuously. Now let's put all of these in the Ginzburg-Landau action. So this F superconductor is going to be equal to F normal plus some d cube r 1 over 2m minus I h bar gradient minus q over c a psi squared plus a psi squared plus 1 over 2 b psi to the fourth, and I have 1 over 8 pi b squared. But this entire thing is in the same integral. And I will unpack the gradient in this cylindrical coordinates. This is going to be some ER del R plus some E phi 1 over R del phi plus some EZ del Z. And so this one and this one will not contribute because there is only angular variable, all others are constant. And therefore, let me write this thing. So let me write it like Fs minus F normal. Actually, these constants are also not important. Let me write it like this. The important term. Because of this, there will be some volume. There will be 1 over 2m, some psi squared. And inside, I need to have, so I have minus I h bar. Gradient only comes with this one, and this is 1 over r. And del theta acting on a wave function like this is going to bring I times n. And this part is 2e over c. Now I'm writing a, which is found here, this a. So this is phi over 2 pi r squared. And plus this 8 pi, some other volume, I don't know if it is like a solenoid, right? All the flux is, all the magnetic field is here. We can write it like b squared, or we can write it in terms of flux squared. Some flux squared, and there's some, I don't know, some beta, some constant here. Good. Therefore, this action is of the form first let me take this r squared outside, and I want to take this 2 pi outside, so this is 2 pi r squared, so this one is gone. Now I can raise bar of h bar, and minus I and I is gone, so this is h n, and I want to write is like hc over 2e, and I want to write this hc over 2e outside, or 2e over c, right? 2e over c squared. And this thing I want to define phi naught hc over 2e superconducting flux quantum. Then this is going to be phi naught, and at the end my free energy is going to be some alpha times n phi naught, okay, n phi naught plus phi squared plus beta times phi squared. Okay. And how do we plot a function like this?
A parabola.
Right?
The shift.
Exactly, parabola, but the dip of the parabola is at n times phi naught, and n can be 0, plus 1, minus 1, plus 2, minus 2. So let's draw this and see how it looks. So let me first something like that, something like that, and I have this parabola, and this is for n is equal to 0, and for n is equal to minus 1 I'm going to have 1 here, n is equal to plus 1 I'm going to have another one here, another one here, another one here, right? So this is, what am I plotting? I'm plotting this free energy as a function of flux. But this is also a parabola, but this beta, because, right, is like another coefficient, and if that coefficient is like that, let me draw it like this. There is like another parabola like that, and because you are adding these two, what you need to do is you need to shift each parabola here. So this one is going to shift a little bit, this one is going to shift a little bit, and this one is going to shift a little bit, and this one is going to shift a little bit, like this. Okay. And to minimize the free energy, right, system is going to go and choose one of these, like some n times phi naught, because this is free energy. System doesn't want to be here, right? It wants to be at the minima here, here, or here, and where n is z. Therefore, we say that flux is quantized, and this is experimentally verified, and it is verified to be quantized in units of hc over 2e. So in other contexts, like quantum Hall effect, there is no e, because in that case there is like single electron quantization. Here we are having a little bit more complicated system. We are actually quantized in units of 2e because of Cooper pairs. So another thing we mentioned earlier, so if we start with non-zero B and above Tc, and then lower the temperature T less than Tc, now you are in the superconducting phase, and turn off B. Now because of Meissner effect and all these flux being constant, there has to be like a persistent current, right? Persistent current. And what you are doing is like you are like nucleating a system in one of these, right here. But because of this potential barrier here, right, the system, because of this barrier, cannot just roll and come down to here. And this potential barrier is high, especially you are at like ultra low temperatures, and this persistent current is conserved by these high potential barriers. And in the experiments, when people calculate the lifetime of these currents, they found years. Sometimes if they extrapolate age of universe for the lifetime of the current, so they are like really persistent and they do not change. And that's how people verify this flux quantization. Now let's think about this geometry. So we have like a minimum, and we have another one like this. And you can put your system in the lowest, right? I can approximate any potential with the harmonic oscillator, and there will be levels here, like something like this. But because this is not perfect harmonic oscillator, they are not going to be equally spaced. Maybe this next one is going to be something like that. Suppose this is my level 1, and suppose this is my level 2. So your system prepared at level 1 is unlikely to escape. Because of this very high potential barrier, it is going to stay there, and that's what we call persistent current. But what we can do, and what actually experimentalists can do, is they can like shine light, and this system which is prepared here can go to here, right? And typically this light is in the microwave region. You shine the light and you go to the next higher level, but you can see this level doesn't have as big of a potential barrier as this one, and the tunneling for this higher state is going to be enhanced. So this is enhanced tunneling, but this tunneling is not single particle tunneling. This is a tunneling of macroscopic matter wave. And the experiment that I think showed this is like Michel Devoret, John Martinez, and John Clark. I think this is PRL 55 1908, and they did this in 1985. And you know these guys, right? Everybody knows. Anybody who doesn't know these guys? They've been celebrities recently. Nobel Prize 2025, and they, I think, got the Nobel Prize for measurement of macroscopic, if I can spell macroscopic quantum tunneling. And this is actually the reason they got Nobel Prize, is this is actually the basis for quantum qubits, right? So they have so-called superconducting quantum qubits. They have like a little bit more complicated circuits than usual LC circuits, and they can encode one and right up and down here, and they can change each state from 1 to down, up to down, or down to up, to encode quantum information. But of course there are a lot of problems. Still we don't have like a working quantum computer, but that's the basic principle for all these exciting developments in the last 5-10 years. I'll have a little bit more to talk about this, but not at the moment. Okay. Any questions? Then maybe I can finish it here. Thank you.